Dear students, today we are going to talk about the famous de Broglie wavelength. What is it, how we define it, and we will also learn how to calculate the value of de Broglie wavelength associated with any body moving with a given speed. Well, what is de Broglie wavelength? It is named after its inventor who introduced this concept, Mr. de Broglie, and he calculated also and proved that theoretically that lambda wavelength associated with any body, any matter, any particle moving with certain velocity, so certainly it will have some momentum because any particle is having mass, and if it is having some speed, so it will have some momentum, and then the ratio of h and momentum p is known as de Broglie wavelength associated with the particle which is moving with certain speed, so that it is having a momentum p. Here h is the Planck's constant, and we have already discussed as it in the equation, Planck's equation E is equal to h nu. A momentum of a particle is equal to mass into its velocity of the particle. So certainly if you use this, refer to this equation, if you take the speed of a particle to be 0, then the momentum of that particle will become 0, and therefore the wavelength associated with that particle will be infinity. That means it is having no wavelength, because the wave is never going to complete. So that means de Broglie wavelength only exists so long the particle is moving with certain speed. Now, how we are going to calculate the de Broglie wavelength associated with some electron which is being accelerated through a potential difference of 54 volt. Why we are selecting this particular voltage? We can select any another voltage, but we shall be using this result in the coming topic, where we shall talk about Davison-Germer experiment, and we will compare the experimental value obtained with the theoretical value to derive some conclusion that the particles moving with certain velocity do possess some wave nature and do possess some wavelength corresponding to that wave nature. So here we are selecting it for 54 volt, acceleration through 54 volt. Now one thing we will also like to discuss, that when some particle is being accelerated through some potential difference, work done on the particle will convert in the form of equivalent kinetic energy. And what is the work done? Work done will be equal to charge into the potential difference across which it has been accelerated. Because you remember the basic definition for potential, electric potential, was work done per unit charge. That means work done is equal to charge times the potential difference. And so we have written the potential difference into the charge which has been accelerated through this will gain some equal amount of kinetic energy given by half me v max square. V is the maximum speed of the electron particles, me is the mass of the electron, and that must half me v max square must be equal to EV, where V is the voltage potential difference across which the electron has been accelerated. Now from this relation you can clearly have velocity equal to under root 2 EV upon me, where here V is the potential difference, and do not confuse with the speed expression V for speed. Velocity, we write it with italic, in the italic form. So V is representing velocity of the electron, and this capital V is representing the potential difference across which the charged electron has been accelerated. and therefore if we know this velocity, we can find the product of mass into velocity. This gives us the momentum possessed by the accelerated electron, and that becomes equal to under root 2 MeV. Me is the mass of, m suffix e is the mass of electron, small e is the charge carried by an electron, and v is the potential difference across which the electron has been accelerated. Now by the very definition of de Broglie wavelength, we can write de Broglie wavelength is equal to h upon Pe. Pe is the potential momentum of the electron which has been accelerated through a particular voltage, potential difference of 54 volt. And when we put the value of these constants here, h is equal to 6.63 nearly into 10 power minus 34 joule second, and divided by under root 2 Me under root V. Mass of electron is 9.11 into 10 power minus 31 kg, and charge on electron is 1.6 into 1.602 into 10 power minus 19 coulomb. And here V is the potential difference across which the electron has been accelerated. Once you put these value and calculate, you will get the value equal to 12.279 into 10 to the power minus 9 divided by under root 54. And that when this factor numerator is divided by root 54, you get this value 1.67 nanometer, 0.167 nanometer, and which when written in the form of angstrom, it becomes 1.67 angstrom. You must be knowing that 1 angstrom is equal to 10 power minus 10 meter, and nanometer is referring to 10 to power minus 9 meter. So this is how we have calculated the de Broglie wavelength associated with those electrons which has been accelerated through a potential difference of 54 volt starting from rest, means it was not having any motion before the acceleration. So that we make sure that the total kinetic energy possessed by the electron is only equal to EV itself, and it was not having any kinetic energy before the acceleration took place. If you have a different situation, you can accordingly put the value of those new case, and you can calculate the de Broglie wavelength associated with the particles. Now here we will also like to verify the dimension of de Broglie wavelength, how it should be in meter. Well, you see, you have the relation de Broglie wavelength is equal to h upon 2 MeV. So when we put the dimension of h, Planck's constant, that should be in joule second, and for mass we must write m, and for charge we write coulomb, and for voltage we write joule per coulomb, because that is the very definition of voltage, that you see potential is defined as work done per unit charge. So work done per coulomb, that means joule upon coulomb, and so coulomb and coulomb cancel each other. We are left with mass, dimension of mass, and joule. So here in the numerator we have joule second. For joule, that is work done, we can write ml square t minus 2, and for second we write t. And in the denominator we have, for joule we write m, that is mass, l square t to the power minus 2, that will be for joule, that unit for joule work done, and then mass is there, so we write mass. Now if you club this together, it becomes m square l square t to the power minus 2, and that whole to the power half is there. And so And so if you take the root and with the square, all the square will cancel the root, and so we get mlt minus 1. mlt minus 1 remains in the denominator, and ml square t minus 1 remains in the numerator, and so finally it becomes L in the numerator only, and that L is nothing but the unit of length, that is unit of wavelength meter. So that's all for today. Thank you and have a nice day.